pH describes a property of water solutions that influence how chemical reactions occur in these solutions. It's not completely clear why it's called pH, but saying the P stands for power helps capture the meaning of the measure, because even though the chemical formula for water is H2O, not all the molecules in a sample of water are in this form. Water molecules are polar, and the attraction between the positive and negative dipoles cause many weak hydrogen bonds to form between individual water molecules. These are weak attractions, but in a small number of cases, the attraction between the molecules cause hydrogen atoms to be pulled completely away from its water molecule to the negative dipole of the molecule the hydrogen bond was formed with. This creates two new molecules, one positively charged H3O molecule called hydronium and one negatively charged OH molecule called hydroxide. These ions exist in chemical equilibrium with water molecules so that at any given time some water molecules are splitting into hydronium and hydroxide ions while other hydronium and hydroxide ions are recombining to form water. pH is used to describe the hydronium concentration in a solution of water. This is an important property of a solution because these ions are very reactive, so a change in the hydronium ion concentration of a solution changes how the solution reacts with other compounds and solutions. The equilibrium reaction is between water, hydronium ions, and hydroxide ions, but for simplicity, the reaction is often written as being between water, hydrogen ions, and hydroxide ions. Hydrogen ion concentrations can vary over many orders of magnitude, so we use a log scale for pH. Mathematically, the pH is calculated as the negative log of the hydrogen ion concentration. This may seem complicated, but it is actually fairly straightforward. The log in this case is base 10, so that the log of a value increases or decreases by 1 for every change of a factor of 10. To see the pattern created by using a log scale, consider the value 10. The log of 10 is 1. If we multiply 10 by 10, we get 100. The log of 100 is 2. Continuing up, the log of 1000 is 3, and so on. The scale also goes the other way. Dividing 10 by 10 gives us 1, and the log of 1 is 0. 1 divided by 10 is 0.1, and the log of 0.1 is negative 1. Stepping down another factor of 10, 1 divided by 100 is 0.01, and the log of 0.01 is negative 2. From here we can see that using log value is a way to simplify the communication of large changes so that we can write negative 7 instead of 0.0000001, and so on. Getting back to pH, consider a solution of water that at equilibrium contains 1 hydrogen ion for every 10 water molecules. The log of the hydrogen ion concentration in this solution is negative 1. If the concentration was 1 hydrogen ion per 100 water molecules, the log of the hydrogen ion concentration would be negative 2. 1 in 1,000 would give a log hydrogen ion concentration of negative 3. 1 in 10,000 would be negative 4. 1 in 100,000 would be negative 5. 1 in 1 million would be negative 6. And 1 in 10 million would be negative 7. Getting back to the formula for pH, the formula multiplies the log of the concentration by a negative 1 in order to get rid of the negative sign, making the pH of a solution containing 1 hydrogen ion per every 10 million water molecules 7. In fact, pure water has 1 hydrogen ion per 10 million water molecules, giving pure water at equilibrium a pH of 7. Note the inverse pattern. The higher the hydrogen ion concentration, the lower the pH. pH is the more common way to discuss the reactivity of water, but there is a related term, pOH, which describes the hydroxide ion concentration in water. Like pH, the pOH of pure water is also 7. These two parameters have an inverse relationship. As the hydrogen ion concentration goes up, the hydroxide ion concentration must go down. This is tied into how chemical equilibriums respond to change. The addition of something to a solution that causes the hydrogen ion concentration to increase will push the water ion concentration balance towards water. And this shift in the equilibrium will result in a reduction in the hydroxide ion concentration. This is how we define acids and bases. An acid is a compound that increases the hydrogen ion concentration when added to water, thereby lowering the pH of the solution. A base is a compound that decreases the hydrogen ion concentration when added to water, thereby raising the pH of the solution. Again, this is important because both positive hydrogen ions, or more correctly positive hydronium ions, and negative hydroxide ions are very reactive, and their concentration in a solution determines how the solution behaves when combined with other compounds or materials.